the demonstration that was described in the packet last class. So they showed you like a little tube and a spectrum and stuff. That is some of the equipment I threw in a tub and brought home. And I have made my cat quite unhappy because I had to block all of the windows to make it dark down here. For when I turn off the lights, it will be very, very dark, so I can show this tube. So Jada, can you hear me now? We'll see. So I'm going to do a live demo, and kind of I'm going to have to switch around with a bunch of external cameras and stuff like that. And then I'm going to actually run a simulation and show you what is actually going on with the electron. So last class and this class are all very much, you know, conceptually what is going on with an electron. On Tuesday of next week, we're going to deal with the calculations of what is going on with the electron. So I just wanted to make sure that we are separating those two things. So the calculations are combined with section 5.3. So the homework is combined. So that homework is not going to be due next week. It will actually be due the week after. So I'll go over the due dates for things at the end of class. So, but that way you know that you've got a little bit more time to work on assignments. So I am trying to hold to the minimizing the amount of things that are due each week for you. So hopefully that's going to help. So let's actually do this thing. So spectrum tube. So I'm gonna stop sharing and we'll show my actual camera here. So
question.
Yes.
Do we need to be taking notes for any of this?
So I mean, that's kind of up to you. I didn't print off or create a specific note sheet. If you want, of course, I am recording, so you can go back and watch any of this, so you can see what I'm doing. Okay, so first off, can everybody see that really big gray hair right there? I'm trying to ignore it. Okay, so this guy back here is a spectrum tube machine. So that's what it is going to do. And then I've got a separate camera here that I'm going to use, and another thing that I'm going to be able to use to hook up to show all of this. So a spectrum tube is literally, it's like that cathode ray tube where it's just it's an empty tube at two ends, but this time instead of being completely empty, it's filled with gas. So I've got 3 different tubes. They look like this. They're kind of fancy. So you can see there's like this little metal coil at one end and then another little metal coil at the other end, but there's not a wire in between them. So it's completely blank in between. So this one happens to be helium, because the first ones they played with were the noble gases, because they started playing with these literally right after they discovered the noble gases, because the noble gases don't do anything. So they literally just started like poking at them to see, it's like, will you do something? And they did do something. They did this. So I'm going to cut some of the lights. And it's a little hard to see this guy because this is helium. And helium's only got its 2 little electrons. And it glows a very, very pale, pale pink. And it looks a little bit purple at the top at the bottom. But that's what it does. It's a pale, pale pink. So that's helium. I'm going to switch out for hydrogen next. Hydrogen is like some super, super weak sauce. It's only got one electron. So it doesn't generate a very, what we would think of as intense color. So it's a really, really pale purple, which you can imagine would be a lot cooler if it was more intense, but it's not. So the most interesting element for all of these is the element that actually gives you the name for this type of sign. And that's that guy. What element is that?
Neon.
Neon. So a neon sign is called a neon sign not because it is fluorescent, but because the original neon signs were made literally with the element neon, which glows this in very intense reddish orange. So the open and closed signs that you see in stores, they're all red because of the neon. The blue portion of those signs is from a different element. It's actually from argon, which glows a blue color. Krypton glows a purple color, if I remember correctly. And then other elements have their own specific colors. So you know the street lights outside at night that are kind of that yellowy orangey color? Those are yellowy orange because they're sodium lamps. Like the same sort of thing where if you put salt in your water on the stove and it boils over and it, you know, the flames kind of like glow this yellowy orange color, it's because that's the color of sodium. So what I want you to think about is literally every single element on the periodic table has its own distinct color. So if you've ever wondered why fireworks are the colors they are, it's because the fireworks are made out of a very specific element and salt that turns it that color. Like that's where it comes from. So we're just gonna stay here with neon, and I'm gonna hook up this separate camera. Okay, so switching. Okay, so you can see it a little bit closer with this document camera, with this small camera. So you can see it's all the same intense one color. Now, if we were in class, I would hand you all these things called spectroscopes. And you'd be able to look at the spectroscope and you could see distinct little lines, and most of those lines would be in this red-orange range. So these things are hard to look through in the best of times, and we are not in the best of times. So we are in this awkward time. So I've hooked up a ring stand with a spectroscope to hook up to this small document camera. And if I can get it to line up, there we go. Yeah. Nope. Okay, so on the screen right now, you see that one intense red line. That is one of the lines in the spectrum of neon. But you see how on either side of it is black? That's because the only color that's being shown is that this very, very distinct red line. Neon has some very distinct red lines, and then it's got some lighter lines that are very hard to see with this camera setup. Yeah, we can't really see them. So I do want you to focus on this middle red line literally right here in the middle of the screen. That's what it looks like to have a spectrum through one of these spectral tubes. So you see this color red with your naked eye, and through the spectroscope, it'll actually block it out into where it's only very distinct wavelengths. So neon is intensely, intensely red. And then it does have some blues and greens, which are too pale to be able to see with this camera. But that's what this thing looks like live. So it's kind of cool. And I wish that we could like all play with them in class because it is a lot more fun, but I did at least want to bring this one home. So I'm going to turn the lights back on and disconnect stuff. Oy. The other thing that you can't hear right now is that that light box is humming. So if you are familiar at all with neon signs, you know, like the electricity that runs through those things is intense. And so like it is some intense electricity. It's marked as high voltage up there on the top, and they're kind of crazy expensive. So I wanted to show you on here what was going on, and then do the demo, the computer simulation. So in the packet we did last class, the packet last class had very much like the circles, right? So instead of thinking through the circles though, I want to use this concept of a ladder, which is what I've created here. So in this ladder, the nucleus is down at the bottom. And so I can go ahead and number each of these guys with our energy levels. So down here at the bottom, what number would we assign this energy level down here?
1.
1.
All right, so that's 1. And we're also going to call this, since it is at the ground of my energy ladder and it's the closest to the nucleus, what state is this going to be called?
Ground state.
All right, ground state. Okay, and then as we move up, this next rung on my ladder would be 2. And then the next one above that is 3 and 4, and then they would keep going up, right? 5, 6, and 7. And one thing to note is that these spaces on the ladder, as you go up into higher and higher numbers, farther and farther away from the nucleus, they actually get very, very close together. So there is a large space between first and second, smaller space between second and third, and then third and fourth. And then once you start getting 5, 6, and 7, it's almost like they're right on top of each other. So if an electron moves up to any of these up here, it moves into an excited state. It goes up. So I'm going to use one of these guys, little magnet, as an electron. So what was just happening, actually let me use a bright reddy orange guy. So what was just happening there is I had an electron that was down here in the ground state. And what goes on is you get some sort of energy that goes in. And in the instance of what we were just using, it was electrical energy, right? I was literally using electricity from the wall to supply energy to that light bulb. And that energy goes in and it goes to this electron. And once this electron takes in energy, it cannot stay on the ground state. So it jumps. And let's say it jumped all the way up here to 4. So it jumps from 1, right? It jumps up to 4. So now it's in an excited state. It did not step 1 to 2 to 3 to 4. It went from 1 directly up to 4. It could go from 1 to 5. It could go from 1 to 6. It totally depends on how much energy it absorbed, but it went all the way up to 4. Now, once it's up here in that excited state, can it stay there?
No.
No.
No, it cannot. That is an unstable place to be. So imagine if you are at the bottom of a ladder and all of a sudden you crawl up to the top of a ladder. It's not stable to just be at the top of a ladder forever. So it's not going to stay there. It is going to come back down. But while you have only one choice of how you go up the ladder, you have multiple ways to come down. So if I went from 4 to 3, well, that would be one step, but I could also go 4 to 2. I could go 4 to 1. I could go 4 to 3 and then 3 to 1. I could go 4 to 2 and 2 to 1. So I have multiple ways to come down, but let's imagine, just for this instance, that I went all the way up to 4 and then I fall all the way back down to 1. So I went literally straight back down. So if I went straight back down to here, what happens to all of the energy that I had when I was up at 4, where I'm now down at 1?
It has to be released.
It has to come back out. I cannot hold on to it, because when you're up here, you do not have the same amount of energy as you do down here. You have less down here. Smaller number means less energy. So I have to give it all back out. And all of that energy that comes back out as light. So I can use different things to give energy in, but I am only going to get energy out as light. That is the only thing an electron knows to do, is to give energy back out as light. So my energy going in can be electricity, it can be heat, it can be light, it can be any form of energy as you think of as energy. An electron can use any of those to move to an excited state, but it will only give back out light. So the color of light depends on what this jump was. So if you went from 4 all the way down to 1, that would be a higher energy color than if you went 2 to 1, right? So if this guy moved up to 2 and then fell back down, that's a different color of light. It's closer to red because red is our lowest color, but that's how this ends up working. Does that make sense to people?
Yes.
Yeah.
Okay. So essentially, what was just happening in that neon sign, or literally any light bulb anywhere, right? So the same sort of thing is happening in the light bulbs in your house, is you have an electron, it jumps up, it falls down, it gives off light. As soon as it gets down, it jumps up, it falls back down, it gives off light. It's like, oh my God, you will not turn the energy off, so I have to jump up and fall back down and give off light. And it's basically like an electron treadmill. If you think of a light bulb as an electron treadmill, you'll remember how electrons are constantly giving off light, because the instant you remove the energy source that is giving the electrons energy, they stop. They don't want to move. They want to stay in your ground state. They do not want to keep moving up and up and up. So that's what that looks like that way. And then the demo, the PhET simulation actually provides a fairly decent representation as well. So this models of hydrogen 1, I don't remember, I know I used it in the video that I made. I don't remember if I had shared that link with you before. It is on the link in this weekly's plan, so you can see everything that I'm going to be doing with it. But basically, this is going to take us through most of 5.2 and 5.3 without the calculations. And then the very, very last part of this demo is what 5.4 is on. So again, it's going to show you basically what I was just showing you, but it's going to show you in the rings from the packet. So you can, it's basically like animating the packet that we looked at on Tuesday. So let me switch to that. Okay.
Ms. Basher,
Yes.
I gotta go because my health teacher scheduled a class at the same time as yours.
Okay.
All right.
Okay. So we've got this guy. And you can imagine that this is the, this is that hydrogen tube that I showed you that looks like super, super pale purple. And if you look at this spectrum down here at the bottom, well, it makes sense why it's purple. You literally have a purple line, you have a blue and a light blue line, and you have a red line. And color theory says if you mix red and blue, what color do you get?
Purple. Purple.
Purple. So my hydrogen tube looked purple, but these purple and blue lines are really, really hard to see in a spectroscope, which is why it wouldn't have shown us like really anything. So that's why I use the neon instead. So I'm gonna take a little snapshot of this. All right, so here's the thing. When they started playing with these spectral tubes, right, they saw that, or Niels Bohr saw that it gave off lines when you were looking at hydrogen, and nobody could understand why. He decided that that was something important to look at, and so he started trying to figure it out. So we can very quickly run through all of the models that we've talked about so far and know which one is not correct. So billiard ball, this is John Dalton. And if we look at John Dalton's model, it's a solid sphere. So shining light on it does literally absolutely nothing. We don't get any lines. He doesn't even think there's any parts to an atom. So that doesn't make any sense whatsoever. The plum pudding model, right? You've got your little electron. So Thomson discovered an electron. So we've got our electron here in this positive goo. And sure, you can shine light on it and it'll bounce around and it'll do stuff, but it doesn't generate any color. So again, Thomson did the great thing of discovering the electron, but he didn't know anything else about it. And nobody else worked on the electron for a while. So Rutherford, and this was, everybody got this right in the video. So Rutherford, yeah, he sucks everything into a nucleus, but then the electron should get literally sucked into the nucleus. And I'm gonna make this go slow because it makes me laugh every single time. So, boom. Okay, so clearly that's not going to generate any color either. So nothing exciting happens until we get to Bohr. And again, this is where most people come to me knowing about an atom. So you've got the red little nucleus in the middle, and you've got a single electrons, and electrons are on these little rings, and that's what they do. So the electron is just moving around, and the way Niels Bohr thought about it was the electrons orbit, right? They circle around, and they'll circle around until something makes them move. So when light makes them move, they jump. So it just jumped out here, but that's unstable, and it fell back in, and when it fell back in, it gave off this little bit of light. So Niels Bohr, watching this, he started seeing lines that look like hydrogen. And it's like, well, that's pretty cool. So we're going to see that what he came up with is going to look like it matches with what we saw at the beginning. And you can see as well this representation of essentially what I did on the ladder, and you can see the jumping and everything as well. So this is great. Niels Bohr solves the problem of where the electron is, right? The electron is apparently orbiting in these energy levels and can be moved to only distinct energy levels with very specific amounts of energy, and it can move back. And this all makes sense, and everybody thinks Niels Bohr is a genius, and he did get a Nobel Prize for this. And when I went to Copenhagen a couple of years ago, I found a statue of him, and I took a selfie with Niels Bohr because that was kind of cool, because why not? But he was not right, because his model only works for hydrogen. So that's kind of frustrating, but he gives us a pretty good idea of what is correct. So again, let me slow this down just a little bit. So the difference between Rutherford and Bohr is Rutherford didn't have a place for electrons. Bohr had a place for electrons. So Bohr could not mathematically explain in any way, shape, or form why these circles were the distances that they were. He could just explain that they must be. So one of the biggest failings for Niels Bohr is he could not actually mathematically explain his stuff very much, and he could not explain his idea for anything beyond hydrogen. So sorry, dude, that doesn't work too great. If you've started looking at 5.3, you come up with this other dude's name, de Broglie. And this is another French guy. And he said, no, no, no. Electrons are not particles. They're not jumping. They're strings. They're waves. And so if you notice, if you look here in the middle, that's not a dot. It's a circle. So I'm going to flip this view. Come on. Come on. No, you don't want to? You don't want to? No, no. There we go. And so if you look, it's like a little string that's vibrating. I actually think it's easier to think of de Broglie's model as a rubber band. You've got a rubber band, and if the rubber band is not stretched at all, it's this tiny little thing. But if you put energy into the rubber band and you stretch it out, that's clearly not stable, and then it's going to snap back in to the middle. And so if you think about an electron as a wave, it makes a little bit more sense how it can only have distinct wavelengths, because it can only have a complete circle. We're only allowed to have a complete circle. So each circle here in this model is a additional complete wavelength. And all of that seems kind of strange and everything, but it still worked exactly the same as Bohr's model. So Bohr and de Broglie, it's like, okay, these both look right. And not only do they both look right, they both pretty much give me the same matching spectrum. So up until this was meh 1920s or so, this is kind of where they were thinking electrons were. They could explain electron behavior in the smallest of elements with the math that we had available, with the colors that they could see through these spectrum tubes and spectroscopes and looking at prisms and stuff. And it kind of went from parlor tricks to a little bit more interesting. But the main thing you need to be able to take out of sections 5.2 and even 5.3 is that electrons will move from a ground state to an excited state only if you give them energy. And if you give them energy, they will move up into an unstable excited state. And when they fall back down to a ground state, which they must do, they will give off their energy back as light. And that light is very specific to the element. And that's it. So what we are going to do next week is to look a little bit mathematically at how they knew what wavelengths we were talking about, how much energy was required to make these things happen, and what frequency of energy was also required to make these things happen. So we're just going to look a little bit mathematically into it. And then after next week, we're going to go into, well, here's what actually happens, because what actually happens is quantum mechanics, which is not this, but it's a little bit close. So that's that. Okay. So at this point, I want to go through reminders of what we've got going and then open it up for questions. So I've gotten, I think, 17 homework submissions. If you still owe me homework, that's totally cool. Just get it in when you get it in. I do have open office hours from 4 to 5 today, provided I make it back from Costco in time for that 4 o'clock class. I will send something out and remind if the lines are insane. But otherwise, 4 to 5 today, and then tomorrow as well. If you have any specific homework questions, you can either, again, send me a remind chat, jump onto Zoom, something like that. There is no new ed puzzle this week, because I would normally do sections 5.2 and 5.3 in the same week. Since we're slowed down a little bit because of our current situation, that means that there's no ed puzzle that's due on Monday. So you still have the same one. It's still full credit. If you didn't do it for Monday night, just get it done when you get it done. Make sure you've read through 5.2 and 5.3, focusing on those calculation portions for Thursday's class. I mean, for Tuesday's class. And you should have a page. in there that is titled Calculations, and it's got some equations at the top. Let me see. In the packet I handed you, it is directly after, it's after the electron, energy, and light packet we worked on Tuesday. It's a sheet titled Calculation Practice. And that is the sheet we'll work on Tuesday. And then after that, you see Flame Test Lab. So we are going to do the Flame Test Lab. We're going to do a combination of me burning stuff here on Thursday and then some other stuff that you're going to play with virtually. So the actual assignment to turn in next week is that lab. That will be the only thing due next week. So get the Ed puzzle done if you didn't already. 5.1 homework was my request for this week. The Flame Test Lab will be my request for next week. And then that homework, which is going to be combined, if you'll notice when you get to it after section 5.3, it says section 5.2 and 5.3 homework. That combined assignment will not be due until the following week. Is everybody with me? We think everybody fell asleep. That's okay.
Yeah, I'm good. I got you. I'm awake.
I'm with you.
Cool. Okay. So if anybody has any questions, you're free to hang out and I can keep explaining stuff. Otherwise, that is what I wanted to get through today.
Have a good day, everybody.
Bye, Miss
Thank
Baskin.
you. Bye.
Ms. Baskin, I'm here.
Who is I'm here?
Kayla.
Yeah, I saw you, Kayla.
Okay.
Okay. The only people I didn't see was Kamaya, Micaiah. I know what her situation is. Jameer popped in. I didn't see Josh or Jayla or Sabrina. Those are the only ones I didn't see. So
Okay. Bye.
okay, bye.
Ms. Baskin,
Yes, Jameer.
can you check your email?
I mean, currently at the moment.
Oh, I mean, just like today.
Yes, I check my email like every 10 minutes. Good Lord. Just not when I'm actively teaching.
All right.
Okay. Okay. All right. Anybody else? Questions? Cool. All right. I'll stop.